Okay, so just a couple more comments before we wrap this section up. So we've got a couple of remarks to make. And so we're going to start with a set of vectors, as many of the statements in this section do. So we're starting with a set of vectors. We've got them indexed x1, x2, all the way up to xk. So k is the number of vectors in this set, and then since all those vectors are in Rn, that means n is the number of coordinates in each of those vectors. And I think I go through that quite often, but this time it's going to be really important to really understand what those mean. So k is the number of vectors in the set S, and n is the number of coordinates. It's the dimension of each vector in the set S. So the first statement we're going to make here is says that if k is greater than n, then you can already say, without any further analysis, you don't have to look into any details, you don't need to look at any of the vectors or what their coordinates are, you can right away conclude that S is linearly dependent, or the way it's worded here is that S is not linearly independent. That's what this statement is saying. Well, why is that? Well, it's kind of like this. If I go back a couple of pages, it's kind of the generalization of this situation, right? We have three vectors, and they each only have two coordinates. So based on that alone, we didn't actually, if we knew that fact at this stage, we could have skipped all this work and just said, okay, well, since there's more vectors than there are coordinates of each vector, the set is automatically linearly dependent. So this is a shortcut that you can use in the future. If you've got a handful of vectors and they're all in a specific dimension, if the number of vectors is more than the dimension, right away, you know they're not linearly independent, so they must be linearly dependent. Okay, and then the second remark, it says that if you've got a linearly independent set, or pardon me, sorry, if you have a linearly dependent set, if you start with the assumption that your set is linearly dependent, then that just means one of the vectors in the set S, this doesn't tell you which one of those vectors is guaranteed to be a linear combination of the others. And so that, what is that? Where is that coming from? Remember this fact? If we started, this was a specific case of three vectors, where we had three vectors. If we assumed that this was a linearly dependent set, then one of those vectors was a linear combination of the other two. The second remark here is just a generalization of that fact. And I'm actually going to add a third remark here. So if S if S contains the zero vector, so if the zero vector happens to be one of the vectors in this list, then S is not linearly independent. And I'm going to let you think about why that's the case. Okay, if you may want to write down an example. Just write down an example of a set containing a few vectors, either two or three vectors, where one of them is actually the zero vector, and check if they're linearly independent. You may want to keep it simple so it doesn't take you too long to do the check. But if you do that check once or twice, I bet you'll start to see why this is the case. But beyond that, I'll leave it to you. And as always, if you get stuck, just reach out and get in touch. We'll look at the details a little more closely.